Welcome to the class. Till time we have seen that there is Rankine cycle and there can be a Rankine cycle basically without any superheat, but it has certain issues such that it will have problem in the turbine exit since the dryness fraction is very low. So we have thought to add superheat. So Rankine cycle plus superheat is also seen, and then it has been seen that the Rankine cycle with superheat leads to higher turbine work output, and then it has basically higher work ratio. So but it has also been seen that it's not always possible to have the superheat existing. If we are going to use the water as source of heat, then it is not possible. If we have flue gases or liquid metals, then it is possible. Then still, if we want to have higher efficiency with superheat, then we have to have certain attachments, and among that attachment we have one thing which is called as Rankine cycle with reheat. So topic of discussion at this moment is Rankine cycle with reheat. So the same Rankine cycle as what we have seen, where we have 1 to 2 as pump, where the water will get pumped from low pressure to high pressure. Once it gets low pressure to high pressure pumping, then it will go to the steam generator or boiler, where it will get heat addition from the external source like flue gases, and then it will get expanded into the turbine, which we call it as high pressure turbine, or what we call HPT, high pressure turbine. In the isentropic expansion of high pressure turbine, we know that enthalpy of the steam will decrease and we will come to lower enthalpy state, which is 4 from the initial state at 3. Here, instead of expanding the steam completely till the pressure of condenser, we will heat the steam in heater again at isobaric condition, and then that heater is called as reheater. So steam will get reheated from station 4 to station 5 or state 4 to state 5. Then this steam is supplied to the low pressure turbine. So low pressure turbine has intake at 5, and then it will expand till the state 6, but state 6 at this moment with single reheat we are reheating only once. So at the single reheat, state 6 corresponds to the pressure of the condenser pressure. So we have condensation from 6 to 1. So we can see that there is reheating in the Rankine cycle, where we are providing once reheating once to the steam, so that we have only two turbines, which is high pressure turbine and low pressure turbine. The point to be noted over here that with superheating we were entertaining, or we were having only one turbine. So complete expansion was taken place in only one turbine, but when we are talking about reheat, we are having two turbines in case of one reheat, or if there are two reheats, then we will have three turbines. So such that we will have multiple turbines for the expansion, and between two turbines we will always have heating of the steam at constant pressure. So in case of single reheat, we have the TS diagram like this. As usual, we have 1 to 2 as pump, and after 1 to 2 as pump, we have heat addition in the boiler from 1 to 2 is pump, heat addition in the boiler from state 2 to 3, 3 to 4 is basically our high pressure turbine, and 4 to 5 is reheating, and 5 to 6 is the low pressure turbine, and 6 to 1 is condensation. So this is how we have our steam power cycle operating when we are having only one reheat. So this is how the steam cycle should work if we expect the reheating to be happening only once. Now instead of one reheat, if we plan to have two reheats, then in such case we can have a schematic to be drawn like this. Basically we will have a pump from station 1 to station 2. After the pump we will have a steam generator from 2 to 3. Then after the steam generator we will have turbine, which is basically high pressure turbine. Then high pressure turbine steam will be heated and then it will be given to an intermediate pressure turbine. So 3 to 4 is an expansion, 4 to 5 is first reheat, what we will call it as R1, and then 6 to 7 is intermediate pressure turbine. Then in case of intermediate pressure turbine we will have second reheat where steam would get reheated from 7 to 8. This is R2, and then it will be supplied to the low pressure turbine, and from low pressure turbine steam would go to the condenser from 9, 8 to 9 is an expansion, and then from condenser it will go to the pump. So this is how the travel of steam would be there. Then in that case we can draw the TS diagram for the steam power plant. In this case we will have usual dome, then we will have 1 to 2 is pumping process, then we will have 2 to 3 is first reheat, then we will have 2 to 3 is heat addition in the boiler, then we will have 3 to 4 first reheat, and then we will have 4 to 5 as second reheat, 4 to 5 is intermediate pressure turbine, 5 to 6 is our second reheat, and 6 to 7 is 3 to 4 is first expansion in high pressure turbine, 4 to 5 is reheat 1, 5 to 6 is intermediate pressure turbine, 6 to 7 is reheat 2, and then we enter into the 8, which is exit to the low pressure turbine or entry to the condenser. So here we will have 1 to 2 as pump, 2 to 3 as steam generator, and then we have 3 to 4 as high pressure turbine, then we will have 4 to 5 as reheat 1, then we have 5 to 6 as intermediate pressure turbine, then we have 6 to 7 as reheat 2, and then we have 7 to 8 as low pressure turbine, and then we have 8 to 1 as condenser. So this is how we will have a schematic or expansion in case if we have multiple or more than one reheats existing. And we will analyze now what will happen if we have reheat into the Rankine cycle. So for that, let us consider the same example where we are told that we have to find out heat and work interaction in the Rankine cycle, which is operating between 30 bar and 0.04 bar, 30 bar and 0.04 bar. Here reheat is told to be single and reheat temperature maximum is said to be 450 degrees Celsius. Superheat temperature is also said to be 450 degrees Celsius. Now all the processes are said to be ideal, and then we have to find out the work and heat interaction and also specific steam consumption. One more point to be noted here, that expansion in high pressure turbine is still dry saturated point. So as per our usual notation, 1 to 2 is pump, 2 to 3 is boiler, 3 to 4 is expansion in high pressure turbine, and as it is mentioned it is still dry saturated point. So, 4 is a dry saturated point, and then 4 to pi is reheat. We are told that this temperature is 450 degrees Celsius. So, now having known this, we can find out. So, initial thing what we know is T1 is equal to, basically T1 is equal to T6 is equal to 302.2 Kelvin, and then we have H1 is equal to HF 121 kilojoule per kg. We can find out pump work by the same formula as what we say, specific volume into delta P. We get it as 3 kilojoule per kg. So, we know H2, which is 124 kilojoule per kg. From the cycle we have P2 is equal to P3. So, what we should do is, we should go to the steam table, we should go to the 30 bar pressure, and then we should go to the superheat part of the steam table. Then we will find out the 450 degrees Celsius for 30 bar in superheat, and then we can know what is H3, enthalpy at 3 is known to us. Parallelly, we will monitor the entropy at point 3. But we know S3 is equal to S4. We have no information about pressure or temperature at point 4. We are just given that dryness fraction at 4 is 1. From this information and known S3, we can find out which pressure has the saturation entropy of steam is equal to S3, that is S4. So, from that we came to know that that pressure is P4, that is 2.3 bar, and that enthalpy is 2713 kilojoule per kg. So, that is how we know the enthalpy at the entry to the reheater 1, or we have single reheater. But then we will go again to the saturated part of the steam table corresponding to 2.3 bar. There we will see the temperature 450 degrees Celsius. For that we will find out the enthalpy at 5, which is 3381. Now we will also monitor entropy at 5. Since entropy at 5 is equal to entropy at 6, we can find out what is the dryness fraction at 6, since we know pressure at 6 is 0.04 bar. So, from that we came to know that dryness fraction at 6 is 0.98, enthalpy at 6 is basically 2205 kilojoule per kg. So, now by all this means we have found out all the corners of the steam power cycle, which is Rankine cycle. Then we can find out turbine work. Basically turbine work is high pressure turbine plus low pressure turbine work. So, turbine high pressure, turbine low pressure. High pressure turbine is H3 minus H4, H3 minus H4, and low pressure turbine is H5 minus H6. So, from that we get turbine work as 1506. We get net work as turbine work minus pump work, which is 1505. Then we can get Q in. The major point to be remembered here that we have two heat additions, one heat addition into the steam generator between process 2 to 3, and also we have heat addition into the reheater between process 4 to 5. So, 2 to 3 plus 4 to 5 Q. So, H3 minus H2 plus H5 minus H4, it leads to Q in as 3890 kilojoule per kg. We know W net, we know Q in, we can find out efficiency. It turns out to be 38.7%. We know W net, so we know 3600 by W net. So, we found out specific steam consumption. So, this is how we can solve an example for reheat cycle. But this example was mainly to compare the different examples in the same, between same boiler and condenser pressures what we have solved. We have seen that there is ideal cycle for Carnot and for Rankine, where we did not consider any efficiency, or we rather consider 100% efficiency of components. We did not consider any superheat or any reheat for Rankine. That time we saw that Rankine cycle efficiency was less for pressure of ours, which is 30 bar and 0.04 bar between condenser and boiler. But as we said that there are components which are non-ideal, 80% efficiency, then we got Rankine cycle as higher efficiency and it has as expected lower specific steam consumption always. But when we added superheat, then in case of superheat, Rankine cycle efficiency is basically improved, and that is 37.5 with ideal conditions, but it got further improved when we added reheat, and that became 38.7. But superheat actually decreased specific steam consumption from 3.84 from ideal case to 2.98, and it further decreased to 2.39 when we consider reheating. So, this is how the evolution or improvement of the cycle is happening when we consider initially Carnot cycle. Then Carnot cycle has to work inside the dome with the constraints of isentropic processes for work and constant temperature for heat addition. Then we had certain efficiency and specific steam consumption, but when we said that no, we are supposed to use with Rankine cycle for the steam power plant, then we got efficiency as 0.035 or 35%, but we got improved specific steam consumption since we do not have to use the compressor, we can use boiler. So, W net got increased. But when we said that no, we do not have ideal components, we have real components with 80% efficiency, then we got lot of decrement in Carnot cycle efficiency and specific steam consumption got improved, rather increased, but Rankine cycle efficiency did not decrease to the extent where Carnot cycle efficiency decreased. But in case of ideal, as we see, if we use superheat, then Rankine cycle efficiency improved further, and with reheat it got further improved. Having said this, what is the outcome of reheat? So, reheating reduces specific steam consumption. We can see that specific steam consumption was 3.84 without superheat, which got decreased to 2.98 with superheat, but with reheat it got decreased to 2.39. So, this is very important point, since we need actually reduced size of the boiler if we go to higher and higher pressures of the boiler. Then reheating increases the dryness fraction at the exit of the turbine. It was expected, since we are adding the heat, so we are going towards the right hand side of the steam cycle, and since we are going towards higher and higher temperature at lower pressures, we are going to have lower dryness, higher dryness fraction close to 1 if we have reheat. This point we should be noting, since we were saying that we were not supposed to have superheat, we were not supposed to have superheat if we are having high pressure water as the source, but in that case we can have reheat possible, since reheat is going to happen at lower pressures, and then we will have sufficient temperature difference, and then in such case we can further increase the efficiency. Reheating increases the net work, since turbine work increases. Then we have increase in efficiency with reheat, as we can see over here, but it is not always possible that we will have increase in efficiency with reheat. We can see that when we can have increase in efficiency. Let us consider the cycle 1, 2, 3, 4, 3, A, 5, 6, 1. Our basic cycle is 1, 2, 3, A, 5, 6, 1. This is our basic cycle. Let us decompose this basic cycle into 1, 2, 3, 4, 1 and 4, A, 5, 6, 4 into these two cycles. This is cycle 1 and then this is cycle 2. Now, when can we have increase in efficiency with reheat? Now, once we decompose the cycle, we can know that there can be efficiencies of two cycles. Cycle efficiency of cycle 1, efficiency of cycle 2. If efficiency of cycle 2 is greater than efficiency of cycle 1, then obviously integration of 1 and 2 will have higher efficiency. What does it mean? This point A need not be here. this point A can be here. So in that case we will have reheat like this. This point A can be here, in that case we will have reheat like this. So we will have basically, in this case we will have reheat like this, in this case we will have reheat like this, and then accordingly we will come down. So point A is not fixed, point A can be anywhere. We can have reheat very close to 4 also. So then in that case we will have expansion like this. So efficiency of cycle 2 has to be seen. If efficiency of cycle 2 is higher than efficiency of cycle 1, then integration of 1 and 2 will always have higher efficiency. What is the problem? Here problem is, as we take the reheat pressure to be lower and lower, then we can see that we have to first add latent heat and then we have to add sensible heat, but in this phase we go too much right, and then in going too much right we will have basically to heat rejection, we will have to start heat rejection at very large temperature, and then cycle 2 would have lower efficiency. Since heat addition is, mean temperature of heat addition is low, mean temperature of heat rejection is high. So due to this lower temperature of heat addition, mean temperature of heat addition, and higher temperature of mean temperature of heat rejection leads to lower efficiency of cycle 2. So since cycle 2 has lower efficiency, if we reheat at lower and lower pressures, Rankine cycle integrated will have lower efficiency. So as it is said that mean temperature of heat addition of cycle 2 is important, and if it is higher than cycle 1, then obviously we will have higher efficiency of integrated cycle. So what is happening? As what we saw, that if reheat pressure and initial pressure means that high pressure turbine pressure, and reheat pressure is the pressure at which we are going to reheat. If it is 1, that ratio is 1, means we are not reheating. So we have certain efficiency. If we reheat at a pressure which is close to the boiler pressure, then we will start getting higher and higher efficiency, and this is how the reheat pressure is decreasing. So we will get higher and higher efficiency. At a particular reheat pressure around this region, which is 0.2, we are getting basically highest efficiency. So these numbers are specific to the example what we are solving, but in general it is true that the initial or higher pressures of reheat, we will have higher efficiency or increase in efficiency. But if we try to have reheat at lower pressure, then we will not have increase in efficiency. We can always see that this is the dryness fraction at the exit of the turbine is always increasing as we decrease the reheat pressure. Okay. So this is the temperature at which we are reheating. If we are decreasing, if we are doing the reheat at higher pressures, then we have higher reheat temperature, and this is decreasing. So the takeaway from reheat part of the Rankine cycle is that if we want to have higher work output from the Rankine cycle, or we want higher net work from the Rankine cycle, we should adopt the reheat cycle. Reheat cycle also gives good dryness fraction at the turbine exit, but we might not have increase in efficiency with reheat. So reheat is adopted in the Rankine cycle to increase the net work. It is not generally adopted to increase the efficiency, since it is not guaranteed. This is the takeaway from reheat cycle of the reheat of the Rankine cycle. So having this part known, now we have covered Rankine cycle, simple one, Rankine cycle with superheat, and Rankine cycle with reheat. The next attachment to the Rankine cycle we will see it in the next class. Thank you.